and you're trying to go from 0 to 100. It's very forgiving, I would say. It's very rewarding. So going from 0 to 100 in Go is fairly easy. You feel accomplished every time you run a program, going from CLIs to APIs, and finally even writing interpreters in Go. But when it comes to Rust, it's very expressive, and it's a feature-rich, huge language. All we get in Go is an error. You all have to face that issue, like, error is not nil, and error have to be passed into different things. That's not the case with Rust. If you get an value, it's wrapped into either a result, which could be a value or an error, and it could be any type of error. You have a lot of control, and there is option. There's no null concept in Rust. The compilation obviously is fast, lot fast in when it comes to Go, but when it comes to Rust, it's slow. And there's a reason why it's slow, because there are a lot of checks that you have to adhere to when you're writing code. Memory is very much garbage collected in Go, but there is no garbage collection in Rust. There is an ownership model, and we will talk about it a little further. When it comes to concurrency, Go uses green threads, or Go routines as we call them. They are lightweight, very lightweight, and under the hood they are then scheduled onto OS threads. But in Rust, everything is dependent on threads. There is a one-to-one pairing between your threads and OS threads. So I'll start with communication sequential processes. This was also talked about yesterday. It was invented somewhere around 1978. It lays out the principle of processes communicating not by sharing data, or rather, we should not be sharing data to communicate. Rather, we should share, or we should communicate by, what the heck? We should be communicating first, and as in terms of channels, so that there is no shared data as such. And as you can see, we have a process communicating via channel C, and we can very much relate it with this Go routines. So I won't spend too much time on this. That's not the crux. So Rust does not like data races. What do I mean by that? Maybe even we also don't like data races, right? Let's see a Go program that will compile and run very much in production. So we start off by creating a channel, and then we have a map. And for those who don't know, maps are not thread safe by design. We start off a Go routine. What we do is we add a value, we insert a value into the map. And then we also send a signal to our channel that, we are done. In the main Go routine, which is, again, Go routine is also there. So we are also sending a data in the main Go routine into the map. And we are waiting or blocking the main Go routine till we receive a signal from the Go routine that we have spawned earlier. And then we finally loop over the values that we have got in the map and print them. No issues, seems here, right? But there are. Here's issue number one. You're sharing your data. You shared your map into a Go routine. What if the Go routine goes panicking? What happens there? We're also sharing the data in the main Go routine, and we're writing to it. So there are two writes happening in parallel. If you run this code, I've run it myself. It will work fine to a certain state, and unless you finally run into a panic. There's a data race. This is a classic example of data race, and you must have seen such code in production. How does Rust do this? I'll port this exact code into Rust. Let's see how it looks. There's a channel. We also have channels in Rust. We have explicit TX means a sender, RX means a receiver. MPSC, if you're wondering what MPSC is, it stands for multiple producers, single consumer. I'll be happy to talk about it very much in detail offline, why there are no end-to-end channels, why there is end-to-one channel. Then we have a hash map, which is again a map. And what we do is we start a thread, very much like a Go routine. We are inserting a value as we were doing in Go, and then we ultimately send a value, a Boolean, to the channel that we had. Next, what we do is in the main thread, which we have, we also insert the same thing as we were doing in Go, nothing fancy, looping over the values and finally printing them. Seems okay, right? It's exactly what we were doing in Go, right? But the only thing that's different in Rust, this whole thing won't even compile. So what's going on? So you see something like this and you feel like, oh, what the heck? This is a lot of information, how do I breeze it? And you must be like this. Let's break it in. So you see something like this. Let's go 1 inch at a time. Borrow of moved value m. What exactly is borrow? We will talk. What exactly is moved? So if you look down, there is a value saying value borrowed here at line 10, where this is the main thread line. We are trying to insert a value at 2 in the main go routine. We were doing so in the main thread. So value is being borrowed after move. So where did the move happen? The move happened at this point. When we started a thread and said move, and we were trying to insert a value into our map. So m is, you had m in your main thread. You said, in our thread, I also like to insert a value. So you moved your m. So there's a concept called ownership. I'll talk about it a little bit. Why does the move occur? Move occurs because m has the type hash map, which cannot be shared between threads. Did Go have the same concept, right? You cannot share threads. They are not thread safe. But did Go stop you from doing it? Nope. And that's your crack. That's where you fall. And that's where you have incidents in production. And people like me who are experienced in on-call, you wake up at 1 a.m. and finally you have to leave family, sit on your laptop for another 3 hours debugging where the fuck that rate condition come from. So let's talk about two concepts, ownership and borrowing. There's only one ever an owner for data. If I own a car, I own it. I can smash it, I can drive it anywhere, I can do whatever I want. There's no owner at all. The RC is registered to one single person, right? You cannot have it shared in your family. Same concept. Ownership can be transferred. I can transfer the RC to another person. That means you're transferring your car to someone else. If they hit the car, it's their problem, not mine. Owners, own value can be borrowed temporarily. We can borrow cars from our friends. I'm going to Lonavala, help me out. So we can borrow a car, we can have their SUVs, and we can all come up together and go for Lonavala trip. Owned values can be borrowed, as I said. Now, borrowing prevents moves from happening. If I'm borrowing for a trip, I don't have to own that car. So I can still use it, I can still smash it, but the bill will be on my friend and not me. So that's the rare difference in borrowing and ownership. When you own a value, you own it. You are the one who is responsible for dropping the value because there is no garbage collection, and you are the one who has to pay, who has the exclusive right to change that value, no one else. But when you borrow it, you only have the readability of it. You can run functions on it, but you cannot drop it, you cannot change it. So in Go, we have seen that there is a shared memory, and we can share data across threads. Nobody talked about it yesterday because there were a lot of talks about Go routines, threads, and whatnot, but nobody talks about data sharing is bad. It's really, really bad. In Rust, you opt into sharing data. How do you do that? You have something like this. Again, I'll start with Rust first, and then also how you can do it in Go. We again start with channels. I've tried to remove a few things so that the code is a little cleaner because it's going to be a long one. We start with the channel. Again, we have a hash map as before. We create an arc. And what the hell is arc? And we have also mutex. I'm sure we all know mutex. Where we have an arc of mutex. Arc stands for atomic reference counting. What's atomic then? Reference counting is fairly easy. You're counting the number of references to something. But what's arc? Arc stands for arc as an atomic reference counting. Atomic relates to atomic operations that are supported by the hardware. They're hardware dependent. Meaning once an atomic operation is in progress, it will never ever be interrupted or stopped in between when it's in execution. So when we do something like this, at line number 5, you see something very interesting like arc.clone. Arc in itself is again not thread safe. You have to clone the value. Let me give you an analogy again. So we have strings in Go also, right? When strings, we all know, are placed on heap. You cannot copy a string. Every time you copy a string, you basically create a new copy in the heap itself. Same thing with arc. What's happening here is the clone explicitly says, I don't want a copy. It cannot be copied either. But you have to create an exact deep copy of this arc and then send it to my thread. So you have arc at line number 4. which remains with the main thread. Then we have tarc, like a clone of arc, which is sent away to the thread. We are not breaking the shared data rule here because we are sending an exact thing, like it's not being owned by multiple people. And then we have mutex. We all know mutex. I won't dive in there. There is a difference between Go mutex and Rust mutex. I'll talk about it towards the end. And then we have what we're doing in the main thread. What we're doing is we get the arc lock, getting a lock over the data that is inside it, and then we are mutating it. At last, we are waiting on the receive channel and waiting for the values and printing them. Looks fair, but I know it could be very daunting, like what's going on, but let's convert it to Go main. This is what it looks like to be writing this, a very similar approach in Go. Let's dive in. So we have this piece where we're creating a channel again. We use sync map. If you don't know sync maps, in the sync package, we have two options, maybe more. Map and mutex use sync map, where you know you'll be reading a lot from your map. We should be using sync maps. And if we want exclusive access to our data, we should be using sync mutex. In our Go routine, we lock the data. We acquire a lock and then ultimately change the data. So we are synchronizing the data. And then when we are moving out, we unlock it and then pass on a value to our channel. Next, we have, again in the main thread, we are locking it, and then we are sending the data to our map, unlocking it, and then waiting for a signal to be received from the main, so the Go routine that we had spawned. Mazaya? Okay. So what are the key takeaways? And it was just a code, and that works. That it compiles and runs absolutely fine. So what are the key takeaways? You cannot switch, dump Go, and straight away switch into Rust. I wish I could. I would love to. But what are the key takeaways? How can I do as a Go developer? What are the things that I need to be careful of? What I can borrow from Rust? Here's one. Run your test using the race detector. How many of you used race detectors? It's about 60–70%, not even close. Race detector is very, very important. The first code that I showed you, if you were to write unit tests about it, run it with a race detector in your CI pipeline or locally, the race detector will eventually detect that there is a race condition and you should stop here. It's very, very helpful. If you're not using it in your CI pipelines, you definitely should. It's very, very important. And honestly, that is the only way to identify race conditions in Go. Otherwise, you have to rely on your conscious. Write concurrent, save code by synchronizing data access. What do I mean by that? Use mutexes. It's very, very important. And be very mindful when you're sharing data. It's just not share data at all. It defies the principles that were laid out by Tony Hoare in 1978. Be safe in Go with sync mutex and sync map. Again, sync mutex is important and is useful when you are writing exclusively to any instance. Sync map is used when you have a read-heavy maps. If your map is to be read more frequently than is to be written, just go with sync map. You don't need mutex. OS does a good job in synchronizing itself. Log data, not the code as a sort. We've seen the example. What we are doing is using mutexes to lock our data. In Rust, we were doing it with arc and whatnot. And yeah, that's the thing. So towards the end of the talk, I would like to give credits to Rust designers for the Rust mascot and the Gopher. These are the credits. Great job done. They have open sourced it. And there are a few references which my talk was based on. If you're interested in Rust, I would highly, highly recommend the last or second last YouTuber who is a Microsoft engineer. He used to be in Microsoft, but now he's into Freemion. He is on the Rust Foundation member. He explains the concepts very, very clearly. John, who is another YouTuber, if you are into Rust already and you want to have intermediate and advanced topics, this is the guy. Dhanyavad. And you can find me here. I'm available. That's it. Open for questions, any.
And he said he didn't want to be politically correct. Okay. So, questions for him?
Okay.
Yes, Ayush. This is the advantage of asking too many questions and being known. Second day of the conference, I can actually identify people by name.
Yeah, hi. Hello. I'm Ayush from Pomatic. So I was just wondering, like, if you got a chance to also explore why did Go didn't have this. First is obviously to have less compile time, but maybe will it hurt to have, let's say, whenever you are using a shared map between two Go routines, and maybe having a option. I'm not sure we have it or not. Just asking. So having a function, do we need to make sure, like, if it's a concurrent text, is don't compile, something like that? So
Unfortunately, Go does not have it by design.
okay.
We rely, so there's a runtime, we all know. The Go comes with a runtime.
Yeah.
There are a lot of runtime checks that happen. In Rust, there is no runtime. I would say it is no runtime. There is a runtime. Obviously, you need something to do something. There are a few things that happen before main. There's a great talk about that as well. So, but Rust is more designed towards system programming. This is to be run in systems that are close to hardware. John, who in his talk mentions that he is developing for British Navy, where he deploys on systems that have memory in KBs. You don't have the space to run a runtime there. So Go is not efficient. So Go was designed to be a higher level language for cloud native stuff, where you have space to run runtime. And what they wanted to have a minimal language that is easy to onboard. And that was by design. And unfortunately, that's the case till today. They are ready to add generics and iterators, but they're not ready to improve their compilation.
Yeah, just the Go community thing, like
yes, it's totally different plane, right?
Yeah, but I think this can be added. Like, this is something which is just a flag away. Like, we can add.
Absolutely, absolutely. And there are more red flags in Go than what we see. So the idea of this talk was to make everyone aware that, okay, we can, if everything that compiles does not run good in production, you have incidents, you have nightmares, and one of the nightmares that resulted in a data race. And right before Gautam connected with me, what is it that inspires you about this talk? That was the incident. I was waking up at 1 a.m. set for 5 hours, then ultimately found that the one engineer had pushed a code which was resulting in a data race. That was the case. Okay. And it was unfortunately not even detected by the DACE detector. We do use it heavily, but it was not detected.
Yeah. Okay, thanks.
Nice. There's another question here.
Hey Gaurav, so in the final Go example, I see that we are using sync maps along with mutex. So I was wondering if we really need to use mutex if we are using sync maps.
Right, that's a good question. And as I said, in this particular example, what I was trying to do, I was writing, you can think of it, I wanted to show both of them. That's one scenario. But as I said, see, you don't need sync mutex here if you're using sync map, because I was writing I have only two Go routines. One is the main one, and there is the Go routine that I was spawning up. In such a small scenario, you don't really need mutex. Sync map will do the job just fine. If you have a scenario, for example, there was a talk about yesterday, Redis and all, where you have a lot of Go channels, Go routines coming up, dumping things into a single channel, and there's a consumer, a lot of consumers. In such scenarios, you may want to synchronize using mutexes and also use sync map, because you're reading a lot and you're writing a lot as well. So to secure your writing, you need sync mutex. For your reading security, you need sync map. So think about it, and according to case by case, you will have to switch. Yeah.
Sure. Couple of questions popping up. Nice.
Hi, my name is Prashant here.
I can't hear you, sorry.
My name is Prashant. In the Rust example that you showed, to me it looked like you're making a copy of the mutex and passing it along. So if it's a totally different mutex, if it's a clone.
Can you be a little, you had said something about mutex in Rust?
He's saying that in the code that you showed, right, it looked as if you're sending a copy of the mutex.
Right.
And that doesn't seem right.
So yeah, that was confusing to me, because it's a totally different mutex if you do
Thanks.
a clone.
It's a good thing that you brought up. So I mentioned in my talk that mutex are present in Go and mutex are present in Rust as well. But there's a huge difference. The overall picture seems okay, but when you have a mutex in Go, if this is my mutex, this is my value, right into it. But when it comes to Rust, this is my value, this is my mutex guard, and then I have a mutex, and over that I did an arc. So what is arc? Mutexes are again not safe for threads. So you cannot send them across threads, because it will again break down the philosophy that Rust brings in. What you can send across threads is arc, atomic reference counting, because Every time you increase a reference, you clone. I showed a clone, right? There was a cloning happening. Every time you clone, a reference counter will increase. So Rust behind the scenes know that there are two things that are trying to modify this data. So you do not pass the mutex actually under the hood. You do not pass the mutex. You pass the arc. Mutex stays where it is. Mutex does not get shared at all. The arc getting shared.
So this is the core essence of immutability in Rust.
Let me leave you with a question, or I can have questions, and then I'll leave you with a question. Yeah, it will be better. Yes.
Okay.
Sir.
All right, guys.
Come on.
My name is Vishal. I'm from PubMatic. So, just out of curiosity, I'm asking. You mentioned about like Rust, concepts of shared memory and move. So, is it evolved from C++ smart pointers and shared memory concept? How Rust was evolved? Out of curiosity, I'm asking. So just for my knowledge. And
Sure.
Initially, I felt a bit offending that you were showing Rust as if it is more advantageous than Go. But as soon as you were able to answer like Ayush question that Rust is more for system programming, not for
Exactly.
like clouds. So yeah.
So, as you said, so Rust borrows, as I said, Rust borrows a lot of things from different languages. This model of what you used the exact word, I just missed it. He said a word about this references being smart pointers is the word, right? Sorry, thank you. So I think C or C++ has smart pointers and they have borrowed it from there. As I said, that was the intention here. We borrow things from Rust and use them with the Go syntax, obviously. That was the intent. So yes, it does borrow a lot of stuff from C++ and that, because it's again designed for low-level systems, performance systems, not just low-level. You can write a Kubernetes operator in Rust and it will just work absolutely miraculously. No issues. But obviously the time consumption to writing it will be huge.
Hello,
Another question. Yeah, there. Right behind.
I'm Samir Oak. Have you considered using RW mutex instead of just mutex? Because RW mutex is a store lock kind of. So multiple readers are possible on the same cache or the same map.
Whereas in Go.
Yes, sing.rw mutex. So multiple readers in that case will be possible. Here what will happen is, once you acquire a mutex lock, the readers are also blocked. The writers are anyway blocked, but the readers will also be blocked.
Absolutely.
So here, if you use RW mutex, the mutual, they are mutually inclusive for readers and exclusive for writers.
True, very true, very true. So the idea here was to emphasize or push a lot of pressure on the fact that stop sharing. It's not about what mutex you can absorb, but rather stop sharing and think about what you're sharing or putting into your Go routines. Thank you, sir. It was a good tip.
My name is Suhan. In your ARC example, the second code, you are creating a new scope with the curly braces, I guess.
Yeah.
So was there a specific reason? Like in the first, there was no
This
scope.
was more or less about highlighting. There's no specific reason
Okay.
for it. Our Rust works just fine even if I don't use it.
And take one last question.
Hi, this is Sachin from Pantheon platform. So basically, my question is like you showed one of the example for the Go. So I was thinking like same thing can be doable using the channels as well, right? I mean, you used like logs and mutex and everything, and that's basically the overall goal of channels to like share your data using channels and don't use like logs and everything because it will going to slow down your overall program. So what's your thoughts on that?
So the intention here is, again, if I'm understanding your question, you mentioned that you're sharing data.
Yeah, because I mean, using mutex and logs, it will going to slow down your program.
It does, absolutely it does. Even if you do a benchmarking, probably using Arc is going to give you a lot of cost. Not a lot of cost, but some cost, because ultimately, so Arc is put on heap. And you're doing heap operations. When you do a reference counter up, a reference counter down, it's an atomic operation, but happening on heap. So it does cost you something. But the idea here is that that cost is fine as long as I'm getting good sleep. I know this this code will not affect or go panicking at runtime. I know for sure. And that's the caveat that with Rust, with Go, that we do not have that kind of surety, right? There are no checks as such. So we as developers have to be mindful what we are doing, what we are putting in our code, and what we are putting in production. This was just an example to highlight a particular scenario. Maybe what you're talking about and what Sir also talked about using RX, Mutex, they are just tools that you have that you should be using. That's the whole, if you're getting those questions, you're getting those thoughts, my talk purpose is served well. That's all I wanted to awake.
Yeah, thank you.
Sure.
Nice. So the essence of this talk is that as Go developers, I know all of us here probably love Go, but it is important to evaluate other languages like Rust to understand what are the nuances that we can either improve or use better in Go. So experiment with Rust and don't let your brains rust. Thank you so much, Gaurav.
The last question I have.
Yes, you're going to leave with a question.
With a question. Food for thought. Think about this. As I shared, there was a Go routine. You have some data shared into your Go routine. There is a lock happening. Mutex is also there. What happens that if that Go routine panics? Does Go give you any tool to recover from that panic? Or is there an error handling that is available? Think about it. In Rust, there is, thanks to the Mutex card. But Go, what happens? Think about it. Search about it. And you will find some interesting stuff. Thank you.
Interesting.